Good evening, students. Pushti sir again with a new topic in gravitation. The topic name is application of Kepler's laws. All of you must be knowing that you heard about Kepler's laws, three laws enunciated by Kepler, and that is in the gravitation. We will discuss application of that law. These are my credentials. All of you must be knowing. You can contact also, number given. So, okay. Now I am discussing a very useful application of Kepler's third law. What is Kepler's third law? The time period of a revolution in a closed orbit by a planet around the sun is proportional to semi-major axis to the power 3/2. Semi-major axis means the bigger axis for the elliptical orbit. Semi-major axis half of the bigger orbit, bigger axis, half of the bigger axis. तो क्वेश्चन क्या है पहले देखेंगे. An object is released at a distance r from the sun. Okay, an object is released at a distance r from the sun, where r is equal to the radius of the Earth's orbit around the sun. The small r is the orbital radius of the Earth around sun. So from that distance r, one object is released. So sun's gravitational attraction force will attract it towards itself. So it will straight come towards the sun. Sun's attraction force will pull it towards itself. So it will travel towards sun and hit the surface of the sun. The question is, how long will it take for the object to hit the sun? What I say here, the radius of the sun is quite small compared to the orbital radius of the Earth about sun. That you assume. So in that case, I can treat the sun as some kind of very small object in the context of this orbital radius, and neglect the influence of the planets. Okay. तो कैसे सॉल्यूशन करेंगे? मैं केपलर से अप्लाई करके सॉल्यूशन करूंगा. ये डायग्राम देखो भाई, ये सन है, ये अर्थ मूविंग इन ए सर्कुलर ऑर्बिट. ये अज्यूम करो सर्कुलर ऑर्बिट. ओके, वी आर अज्यूमिंग ए सर्कुलर ऑर्बिट इन दिस. S is the sun, E is the earth, and this is the orbital speed of the earth, VE. ms is the mass of the sun, r is the orbital radius of the earth's orbit. Assume the circular orbit of the earth around the sun, and also assume that the sun is stationary, because sun's mass is much bigger than the mass of the earth, so we ignore the reduced mass concept. So take the sun itself as stationary, negligible motion of the sun. So we need not bother about any reduced mass or any common center of mass. We don't bother about it right now. So Earth is just moving around the sun in a circular orbit, that is assumed, and sun is assumed to be fixed, to be stationary. So with respect to a reference point fixed to the sun, the orbital speed of the Earth is how much? You must be knowing this, Gms by small r root over. है ना? What is time period of revolution of the Earth around the sun? This is what the Kepler's third law is. In place of r, this is A. A is the semi-major axis for a circular orbit. semi-major axis, semi-minor axis, all are equal to radius of the that circular orbit. So that's why T is proportional to r to the power 3 by 2, or proportional constant is 2 pi divided by root over of GMS. And we know this is 365 days, almost. If any object is given a tangential velocity Vp, कोई ऑब्जेक्ट को मैं अगर ये एक टेंजेंशियल स्पीड दूंगा, दिस इज द प्लैनेट, ये let us take this, not B, just take it as a, this is the planet. Okay, if given a tangential speed, what I wrote here, just see. If any object given tangential velocity Bp is Be, same as the speed of the Earth, orbital speed of the Earth, which is the GMS by R, at a distance R. At a distance R is equal to orbital radius of the Earth. कोई अगर पार्टिकल को हम लोग GMS by R root over का वेलोसिटी देंगे, इस टाइम पर रिवोल्यूशन will what? It will move in the circular orbit because it is not affected by the mass of the revolving particle. So whatever the Earth or a 1 kg block, whatever that, if they give a tangential velocity root over of GMS by R, R is the distance, R is the orbital radius of the Earth, then time of revolution of that particle will be 2 pi by GMS root over into R to the power 3 by 2, which is 365 days. Okay. ऑर्बिट इज सर्कुलर. अगर Bp लेस देन GMS बाई R होगा, लेस देन GMS बाई R होगा, ये Bp जो है, Bp लिख देता हूं, ये Bp, P means that particle, that one. If it is GMS by R, it's a circular orbit with radius R, which is the orbital radius of the Earth. If the Bp is less than GMS by R, the path will be elliptical, smaller than the circular orbit. Elliptical, smaller than the circular orbit. Yes, like this. These are the paths. All these are given smaller and smaller velocities. So they become elliptical path, and the smaller the projection velocity, the tangential velocity, the narrow will be the elliptical path. If I give a velocity which is greater than GMS by R root over but less than 2 GMS by R root over, 2 GMS by R is that escape velocity. So it will be and again elliptical path, but the path will be lying outside the circle. It's bigger than the circle, ellipse, but bigger than the circle. The bigger the projection velocity, greater the more, as become more and more, it becomes greater and greater than GMS by R root over. The ellipse will be bigger and bigger. Until what velocity? Until 2 GMS by R. Within that, it will be still elliptical, but bigger than the circular orbit. If it is equal to 2 GMS by R root over, then that will be a parabolic path, and it will not going to make a closed orbit. It is going to escape. It is going to escape to infinity. Sometimes we call this as V escape from a distance smaller. If Bp is greater than root over 2 GMS by R, then path will be hyperbolic. Obviously, the body goes to infinity. But at infinity, it will have still some kinetic energy, where in this case, we go to infinity, but at infinity, the kinetic energy becomes 0. Now, let us come to the question. Question क्या था भाई? अभी question भूल गए हम लोग. Question ये था, how long will it take for the orbit to hit the sun if I just drop it without giving any tangential velocity? So if I go on giving smaller and smaller tangential velocity, it is going to move in smaller and smaller ellipse. And finally, if the tangential velocity tends to 0, it will become a almost matching with the ellipse will almost match with a straight line. We call it a degenerate ellipse. As the velocity of the projection decreases, the elliptical becomes narrower and the length of the major axis becomes smaller and smaller. Yes or no? Sun's position not be changing, but this major axis, the distance becomes smaller and smaller. And when it is almost, the projection velocity almost 0, the tangential projection velocity almost 0, it will travel in the narrowest possible elliptical orbit, which is nothing but a straight line, where the extreme end of that ellipse, extreme end of the major axis of that ellipse will match with the sun position. Understood this? So the sun will be at the end of the straight line. The straight line is nothing but the major axis. Okay? And the major axis is distance. Here the major axis is distance from the release point to the sun. The sun will come to the end of the other extreme point of the elliptical orbit. Okay? So the focus will almost match with the perihelion point. Okay? So in this degenerate ellipse, which is nothing but a straight line, what will be the major axis? R. Semi-major axis R by 2. So what is the time period going to on this straight line and coming back? One time period will be how much then? Same major axis R by 2. So T, as per the Kepler's third law, 2 pi divided by root over GMS, A to the power 3 by 2. But A is how much? R by 2. So this is 2 pi by GMS root over R to the R by 2 to the power 3 by 2. That is R to the power 3 by 2 by 2 to the power 3 by 2. That's 2 root 2. 2 root 2 को बाहर ले आओ. So 2 pi pi GMS root over R to the power 3 by 2. R is the radius of the Earth circular orbit. But this nothing but the time period of revolution of Earth. So that is 365 days divided by 2 root 2. This is the total time period. Total time period means it goes towards sun and returns back. But my question is, what time it take to hit the surface of the sun? So just one way path, that is half the time period. So to hit the sun, the body travels from the release point to the sun, that is half the revolution. So the time taken will be half of the time period, that is half of this time period is 1 by 2 root 2, 365 days, uska half. So that becomes 1 by 4 root 2 into 365 days, almost 64.5 days. So to the time taken, that is T is equal to capital T by 2, which is 64 by 5 days to hit this. So this method is much easier than the normal kinematics method. Kinematics method में क्या करेंगे? We will calculate the force, then acceleration of the particle, then we'll integrate to find for the time taken to reach this sun. Okay, that will not be any different from this value. Okay, so but that will be quite lengthy. So second observation here, I am making the influence of the planets have been neglected. Other planets, they don't exist. That is what we assume here. Okay, so this is a very nice question. Very, without doing any complicated calculation, we just applying the Kepler's third law, we could arrive at this result. Are you clear? Very nice. So we will be discussing some more questions relevant questions. Again, next. So this I discussed in the topic called gravitation. So this is the topic. This topic is gravitation. Okay. All of you must be knowing gravitation. I am observing that there are many questions are coming from this chapter gravitation, which is a small topic, but as far as the at least the JEE mains is concerned, this is quite significant, this topic. Am I clear? So go through it again and again. This whatever I wrote here, the VP, all this should be, you should know them. You can prove this, the conic section, the path will be a conic section. Any particle which moves under the influence of a central force which obeys the inverse square law, it will trace a path as that which is a conic section. Any particle which is moving under the influence of a central force obeying inverse square law, the particle will move in a conic section path. That can be ellipse, parabola, hyperbola, or special case of ellipse is circle, like that. That proof we have not done in our syllabus, but that's not a difficult at all, not at all difficult. Okay, you can refer to one more discussion in this gravitation in my previous discussions, in my previous uploaded video lectures, which is quite elegant and quite useful. Okay, for the time being, I think you are quite clear about this. So we'll stop here today. All the best for your upcoming examinations. Go through my lectures. It will help you in cracking your competitive examinations, and it will build up your strong foundation. It will build up strong foundation in your physics so that you will fear less. Okay, the less you fear, the more confident you become, and the better success rate you will have. All the best. Thank you all.